So hello everyone. I'm surprised to see so many people since Venkat is in the other room. But yeah, awesome. You guys are here. So, you know, the thing I hate about conferences is that people tend not to leave the talk if they find it boring or maybe too difficult or maybe just too easy. And what I even hate more is when speakers will not tell you enough what the probable topic will be on the presentation. So this is what I did for this talk. So I gathered like 4 different kinds of the Spark developers that might be here. The first guy, he's the newbie. Like, he heard about Spark. Apparently it's something cool, but he doesn't know anything about it as whatsoever. That's not the talk for that guy. This is me 9 months ago. I've been using Spark for like tutorials and stuff like that, and I said, yeah, this is awesome. I'm gonna conquer the world with it, right? This is probably me right now, like saying, yeah, okay, I've seen the dragons. It's not always that awesome and that perfect, but I think I can handle. Or maybe I'm somewhere in between those two. And the last one are the Spark hackers, contributors, and guys who probably should be doing this talk instead of me. Those guys probably not here. Anyway, all right. So there are 4 things I would like you guys to take away from this presentation. Like, if you take anything from this presentation, then please be those 4 things. So I would like to guys know how Spark works internally. Like, have at least some notion of it, how it's work internally. Have the courage to look at the code implementation of Spark, because the majority of problems that you will encounter can be easily understood if you actually look at the source code. And the source code isn't that hard if you read it. And hopefully I will be able to show you this, guys, today. I would also like to give you guys some notion of how to write efficient code, because I will argue like some percentage of problems that we will encounter are mainly because the code is not efficient. And the problems that you will see are basically because we didn't write efficient code. And the last thing would be to basically some abilities to monitor Spark, how it works, to know the problems are coming before they actually arrive on production or on staging environment. All right, so two words about example use. Like, normally if you go to Spark presentation, there's gonna be like word count, right? So I thought this is something that we're gonna do today. So I would imagine that we have some awesome application event sourced. Any of you guys been on the Greg's talk today? So this application writes events to a journal, and we would like to eventually make some calculation on those events. So we have a Spark cluster, and we reach for those events from our journal. No matter how, we can drop them to files, or maybe reread them as streams, whatever, and we do some calculations on those events. And events will be quite simple. So we have an ID, we have a date when the event occurred, type of event, and some additional data if needed. Simple as that. All right. So let's look at the sample code that we could write in Spark. So we read those events from our journal. We group by them by the date of when they occurred. Then we're gonna map this group, saying that for every date, give me the size of how many events actually occurred during that day. Then we will filter out all the events that happened before 1st of March 2015. Having that, we will take a sample of sample of 300 results and maybe print at the console. Hopefully that's comprehensible. This is our example that we're going to work on. All right. So before we go into the code, my main question that we should answer for the first thing is would be what the RDD is. And you guys probably know RDD. RDD stands for Resilient Distributed Data Set, which probably distributed data set is the thing that we should be focusing on. So we have this notion of our data lying somewhere around the cluster, and we think of it being distributed among our nodes within our cluster. That's our notion. That's the abstraction that RDD gives us when we create our software. Actually, the abstraction is correct if we want to like reason about our code, but this is how not internally RDDs are created. So RDDs they are made of 5 things, but 3 of them are important. 2 of them are just some kind of optimizations. So the first thing that RDD needs to have is a pointer to its parent. So if I am some kind of filter RDD, and I was filtering data from Hadoop RDD, I have to point to Hadoop to know what exactly my father was bringing from HDFS. The other thing we need is the idea of how the data is partitioned within the cluster, how the data lies around all our nodes. And the last thing would be how to actually evaluate data from the cluster. That's the main 3 things that we need to have to compute the RDD. So let's look at the very first one, the second one, sorry. So how the data is partitioned. So what is a partition? Partition is basically a subset of some data within our distributed collection. And the question that we need to answer is, well, each RDD has to provide implementation for this method, get partitions. Why partitions are so important? Because basically partitions provide us this, those are the guys who allow us to do computation within the cluster in a parallel way. Because the amount of partitions that you have, they will be run separately on each node, and that's the level of parallelism that you will get from the Spark, the number of those partitions over here. So the thing is that the way the partitions are provided is typical for each of the RDD that we have. So given the example, imagine that we have Hadoop RDD, and the question would be how Hadoop is partitioned. Well, Hadoop RDD is partitioned exactly the same how the chunks within the HDFS file, HDFS system are partitioned. So, for example, imagine this is our RDD, the abstraction that we have. We have our 3 nodes, and some chunk of data lies on the node 1 and 2, and that will be one partition. Some other data is lying over here, here, and here as well. If we look at the code, it is pretty straightforward. There's a lot of weird code, but the 2 lines are probably the most important lines. So eventually, we take splits from HDFS system, and based on that value, then we create an array of Hadoop partitions where we take each split and provide it as a parameter to the constructor of this class. And this is what we return. If we, for example, take map partitions RDD, this is actually RDD that will be returned by the filter method. Then we will, if we add this question, how those guys are partitioned, then we will learn that map partitions RDD inherits partition information from its parent. What does it mean? In code, it means just this. Take the parent and return partitions as parent has it. Pretty straightforward. The second thing would be the parent itself. So this is the code that we wrote. But Spark doesn't give, he doesn't care about the anonymous functions that you provide internally into calls of his API. He just doesn't care, because he looks at your code, at RDDs, in a way that he's wondering which methods from the APIs are you using, but things that are internally inside, well, he doesn't care. It's just basically some functions has to run over the data that he has in the distributed class, the distributed data set. So he will look at your code like this. This is exactly what Spark sees. So we have our Hadoop RDD with some data already partitioned. Then we're going to do a group by. Then we have map and filter. And we know we have this notion of parent. So each RDD needs to know who was his parent, because each RDD eventually will have to calculate at some point your values, right? If you call collect on that RDD, he has to traverse back to his parent to actually start the calculation and go back forward. But this is not how the parents are provided in Spark. There are actually 2 ways that you can provide information about your parent. There are two types of dependencies that you can have within Spark. One is called narrow dependency, and the other would be called wider dependency. Wider dependency is a kind of dependency that you are saying that I have my parent, but in order to get the information from my parent, the shuffling has to be occurring. So shuffling, like data flying around the cluster, putting data into different nodes than they were previously before. So whenever you're doing shuffling within Spark, you have the narrow dependency. And the other type of dependency would be the one called narrow dependency, which is like this. It's really simple, it's pipelined from, so it's not that the whole RDD is having pointers to its parents. It's more like each partition knows exactly the pointer to the partition from the previous parent. And that's actually one of the things why Spark can run so fast, because those narrow dependencies allows you to pipeline calculations, because this data depends only on that data from the previous calculation. It's lying on the same node. There's no data flying around the cluster. So this thing in Spark, this is exactly what we call task. So if you have your logs in Spark and you see something called task, this is exactly it. Spark will look at your calculations and it will actually think of it as a one calculation. Because even though you were doing filtering and previously mapping, and you had some previous data from previous shuffle, from group by, from Spark point of view, you are just running on the same set of data on exactly the same node, and you are doing first filtering, first mapping, and then filtering. So this thing can be run in parallel without dependencies on other data within the cluster. So all those guys can run in parallel. Here we have tasks, but once they are finished over here, they all have to wait for each other before the shuffling occurs, because the data has to fly around the cluster. So they all have to just wait here. Like if this guy is the last one trying to finish his job, they all have to wait for him, then shuffling occurs, then we have the other calculations running. So Spark, as I said, look at this from point of Spark, it's simply a single calculation. From his point, he has to read some data from disk, then the shuffling will occur, and then he will do some another kind of calculations, whatever the developer, the user provided. And this is what we call in Spark stage. So think of stage as a super set of calculations that can be run in parallel on one single partition within one of your nodes. All right. And from the point of understanding what's going on in your program, you also have to remember that. All right, so if you look at any examples in Spark, like tutorials, this is actually not how the image is created. The arrows are going from this direction to that direction, because we tend to think that we just finished the stage one, and then we are pushing data to our nodes. We are, shuffling, grouping by key or whatever. Actually, what happens is once that is calculated, that is being written to disk, and then that data is being pulled by the second stage. So the second stage kicks in, sees the data already partly partitioned on each of the nodes, and puts that data in. So even though we're thinking this data going this way, the communication is the other way around. So we have two notions of shuffle writes and shuffle reads. And these are the values that we have to take consider. Like if you having like read some amount of data and you thinking that you should be working on like maybe 3-4 megabytes on the second stage, and like there's 3 gigabytes on the read and write, and then you know something's not wrong and something's going on within the calculations that you're doing. All right, so till now I was just showing you guys that this is something that we can read if we know how the API works. We know that group by will create a shuffle, so we can reason about this code. We know that probably we're going to have 2 stages here, but because we are lazy, I mean at least I am lazy, there's actually a method that you can call on your RDD, which is called toDebug String, and that gives you the overall idea of how this acyclic graph was created. So we've seen that we read some files from Hadoop. The number that you see here, number 6, means the amount of partitions that how this RDD is partitioned, so how many partitions are within the RDD. And then we see there's the step in the tree. So we see that this thing over here, those 3 calculations will create yet another stage within our calculations, and we see that the amount of partitions dropped from some point, whatever, but it dropped. All right, and the last thing is the question how to evaluate the internal data. Because you guys know that in Spark we have operations and we have actions. Operations are lazy calculations, transformations are lazy operations, the one that we can call on our RDD but will not trigger the calculations. And the actions are actually one that will trigger the calculations, which will run over the cluster. The question is how those actions actually work. So let's call it an action on our RDD, which will be collect. And all actions internally will use one and single method, which is called run job. So if you understand how this method works, you will be able to read like every single implementation of any action that you have within the Spark API. So run RDD takes 3 parameters. So it will, run job will take 3 parameters. The first parameter will be the RDD that we are trying to evaluate. The other parameter will be a sequence of partitions. So we are saying which partitions are we interested in to make the calculations. And the last parameter will be a function which will take an iterator of values. So this will be like values within each of the partitions. And what should be the result calculated for each of the partition. And the result that we will have will be an array of those values. So if we provide 3 partitions, this function will be run 3 times for data of each of one of those partitions, and the results will be packed as an array. That's basically what it does, nothing else. And if we have right now a collect function, then writing a collect is really easy at this point. Once you have this method implemented, writing collect is easy because you provide yourself as an RDD. You're saying that for each iterator, just change that to array, and having that result, you just have to concatenate all the results within the array because you have array of arrays, right? And now you have to like concatenate results to make one single array, which you will return as a result. And like count would be exactly the same. So then again, you pass yourself, and you have some utilities that could generate size for each of the partitions, and all you have to do at the very end with the result that you will get, which will be array of integers, is to run sum on it, and you have the value. So once you see, so like we write, if you look at the output, like you're running your Spark program and you're having some problems, you will learn about stages. You will see stages. You will see tasks, and you will see jobs. So like we right now discovered like those 3 main nouns within the Spark that you guys as developers should know. The thing is, it's sometimes people are not aware, like why do I trigger one action and I have more than one, don't have one job, but multiple jobs. So the thing is, most of the time for each action that you will call, you will have one job running. But there are some actions, like for example take, and take is way more complicated than this code. I just took like the most important part. But what take does is it gives you like overall idea of how the data calculated within your RDD looks like. So if you have like 100 partitions, writing take first 100 for my first partition would not be like really wise because there are other data within the cluster that you have to provide. So the idea was to run jobs separately for different partitions and then combine them together. So this code over here will be, let me look for it. It will be, here. So it will be called recursively. So you have few jobs running for this one action. So don't be surprised having some multiple jobs for a single action within your program. All right. So having that knowledge, let's see how it works in real life. I made some animations. So this is our code. This is just to remind you you guys how it looked. So we had 2 stages, and let's call count on it. So first stage, this will be a timeline, right? Time is passing by. This is our cluster. Within the cluster, we have some data partitioned. So this is our cluster, some data partitioned, and these are our nodes within our cluster. So the first partition is being calculated on node number 1. The same moment, the other calculation kicks in with the second partition on node number 2, and the same thing happens with node number 3. Those are being calculated, results are being returned and written, ready to be shuffled. So we take another partition, we're done. After that data was calculated, what will happen? You guys know? Shuffle, yeah. So shuffle must happen. It will take some time. Eventually, that data is flying around the cluster. And we have a new stage right now running. But this time, we only have 4 partitions for some reason. So we take first partition, run it on node number 1, second partition, third partition, and fourth. Yeah, and this is calculated. All right, we have our result. Awesome, this is running. No bugs, that's good. But this is really, really slow. Because if we look at it, we have filter method at the very end of our calculations. We've been having data flying around the cluster by simply running group by to have it filtered at the very end. You do have to remember that Spark will do some optimizations for you, but he does not know whether it is safe to move that filter up because he doesn't care what's the internals of the function that you provide. So this will work slow, but only if you move that filter method up, this grouping will be really, really fast. Because you can imagine that we have like events from the last 3 years, and we are only focused on the events that were happening since 1st of March 2015. All right, so that's the very first refactor that we can do. And the lesson to remember is that I will try not to repeat myself. This is probably the last time I'm saying this. Spark doesn't care about your code. So you have to think about the logic that you provide to make it efficient. The next thing is that we have, after shuffle, we received 4 partitions, and we have only 3 nodes within our cluster. So we reach a point when we are running in parallel 3 calculations. This is awesome, but once the fourth one is waiting for a 3 node. Once those will finish, and as you can see, they will almost finish in the same time, we will be waiting this amount of time for just the last partition to be calculated. And at this point, we'll be not taking any power from the cluster because this will be running on one single machine. So it will be equivalent just to calculate it on a single machine. So how we can overcome this? Well, we can provide, and there's a parameter that you can provide as a second parameter to method group byte, which is called partition size or number, something like that. So what we are saying is that, awesome, when you're gonna do a shuffle, when you're gonna group by some key, we would like to have this number of partitions within our RDD. And at this point, this will run in parallel. We take the power of our cluster to run the calculations. This is where we were before. This is when we will finish the second stage. So the question might be, can we, instead of providing 6, provide 12 or 100 or 1,000? Where should we stop? So there's the answer to it, and I will answer it in a second. But you guys have to remember one thing, is that you should have at least twice, this is the default for if you read Spark documentation, they will tell you by default, provide at least twice amount of partitions than the overall number of cores that you have within your cluster. So you have 4 nodes. If each of them has 4 cores, then 16 16 times 2 is 32, and that's like the minimum that you should have. But we'll come back to this topic in a second. All right, and the last thing that we could look at is actually, this thing over here, grouping by and running map, is called an antipattern in Spark. Yeah, it's a framework is mature enough to have antipattern, so we're reaching a new level. So basically, imagine that what we are doing at this point is, even though we filtered some data, there's still some data that we have to, well, be making calculations. And what we do at the very end, we are reducing. So we have for each key, for each date, we have some list of events. But at the very end, we are just interested in the size, like how many events were per day. So we are reducing at this point. So first, we travel all that data around the cluster to group by, right? And then we are reducing. So if you guys have been using Hadoop, there's this thing combiners, and we also can use it in Spark. So the idea is simple. Instead of first flying data around the cluster and then reducing, we could first reduce locally our data. So I could first calculate the size for each of those partitions, and that could be run in parallel for each of the nodes without data flying around, having partial sums for each of the day. Then I can push that data around the cluster and make the final calculations. So just to give you the example, instead of running group by and then reducing, what we could do is say we tell to Spark, the first time that you encounter a key from the group by, the key that you haven't seen, run this function for the value. So we just run for the first event, we say return 1. The other thing is that the other function, the function that we provide as parameter is that we're telling Spark, if you've seen this key before, then to the value that you returned, which will be counter, run this function. So you're just saying counter plus 1. And those two functions will be run in parallel on each of the nodes. And then having those values calculated, so we have partial counters calculated, then Spark will actually do the shuffling, data flying around the cluster, and it will simply call this function as a final reducing function. So it will just reduce the partial sums. Hopefully, this is comprehensible. Sorry. Yeah. Yeah, it is. I mean, reduce by key is implemented using combine by key. A combine by key is the most general function there is. Majority of functions within Spark are implemented by combine by key. So even group by key is implemented by combine by key, but it will make your data flying around. But reduce is also the same thing. So it's like fold will give you the value 0 and stuff like that. All right, so again, about partitions. So you guys might wonder how much partitions should I have, and what will happen because here I could provide partition because I was grouping by, but what happens if I'm not doing a shuffle? So there's a method called repartition, and that method will actually make a shuffle for you, but it's sometimes something that you want to do, because if your numbers of partitions is 4 and you have 100 clusters, running this probably not a good idea. A good idea would be to repartition the data and then run your calculations. There might be situation that you actually need less partitions than you had before. So imagine our example. We had this many partitions, 1024. We filtered that data, and imagine that we have events from the last 5 years, and we're only interested in the last 3 months. So at this point, we will probably end up with, 1,000 partitions without any data, empty partitions, and maybe 20-something partitions that actually have some data. So at this point, it's actually quite wise to minimize our size of our partitions, because the number that we will get 64 partitions, but we will have data in that partition. If you have empty partition, Spark will take it, put it to a node, deserialize the task, runs your function against empty data set, and returns the value. That takes some time, which is basically stupid because there's no value that you actually need from this calculation. So, and the cool thing is that calling this method will not create a shuffle for you. So it's something something worth noticing. All right, still have some time, so I can show you a little bit about how the stuff that we just saw from the Ferkel point of view, how we can actually see it in action. So the things I was showing you guys was basically, I've read some books, I've read some blogs. All right, awesome, but I have a problem in my program. How can I look for the solution? So the first thing that you always should look at is this UI that is running on master. So if you go to master, and by default it's port 8080, you will see some basic knowledge about the cluster that you are having. So we see that we have 2 executors. We can see how many cores, how many memories we can use for each of those. Some pretty basic stuff. If we run our application and we go somewhere inside here, we'll get a little bit more knowledge, but not enough. The cool thing is this button over here, Application Detail UI. So while your application is running, it's creating a new server, I would say, a new port with information just from the job you are running. If we look at it, we have some additional informations. In version 1.4, there were also some graphical UI things added, which some people might find useful. So if we go to our job, we will see that there are actually 2 stages. One stage already completed. We see duration of that, how much time that stage took. And you have 1 stage active, which is still being calculated. But there, you'll find in the left upper corner 2 links. First link will open like a graphical visualization of how your job is running. So you will see that at what point the executors were added, which stages, the blue ones, were completed, which ones are running, how much time they took. Also, you can get the information that the one that we see from the console. Now you have the cool UI with graphs, so you see how the stages are actually composed, how the data is flying around, and stuff like that. So maybe this example is really, really easy, but if you have more complex ones, this is might something useful. Like you run your calculations, and then you look at the graph, and it's horrible, and you know you did something wrong. All right, so we can then go to one of our stages. If you go to the one that is running, you will not receive that many results, but if you go to the one that's completed, then you get some additional stuff. You will also get this DAG visualization. This is actually something cool. It was added in version 1.4. Is at this point, you get information like what was the scheduler delay, what was the time the task was deserialized, the actual time of calculations, and at the end, the time for shuffle writes. So not for the whole shuffle, just to put the data onto disk. So if you have, for example, if this green thing would be much slower than the other guys, the blue, the red, and the yellow one, then you know that probably you have the really, really small partition. It took more time to deserialize the task, schedule it, and shuffle than actually to calculate anything. This is something quite useful, because if you go to any Apache Spark talk, they will tell you can now program in Spark the functional way, right? Because being functional is right now really, really cool. And you can, but you have to remember about problems that you get on the JVM while creating a functional code. And the problems might be with GC. So it's quite useful to also look at those statistics. So how many, sorry, I didn't see, oh yeah, GC time. So like the average and stuff like that. Because for this task, well, this was quite awesome. So like the task took around 6 seconds, and 20% of a second was only for GC. So this is actually quite a good result. But if you have like, if you read some data from Cassandra, and then you create your own classes, and then you manipulate those classes, and then you reduce. So at some point, if you're running it for millions of objects, at some point you might end up with situations that the task is running for 3 minutes and minute and a half is only a GC. So it's something worth knowing and looking at while you run your code, even in development environment. And the additional matrices that you can work with, you can turn them over here. They just give you additional stuff, like you can right now understand how reads work and writes work within the shuffle. So if your shuffle takes a lot of time and shouldn't be, this is probably the place to look for, like how many data am I spilling to disk and how many data is being read by the next stage. The sad thing about Spark, this application UI, is that once the application stopped running, if you try to open it, you will learn that you no longer get that information. But they will tell you also that you could turn on this variable Spark event log enabled. And this is something cool, because what Spark will do once this is turned on, they will throw events, like each executor will throw events at you, saving them to disk. It's really, really fast. It's not giving you any problems with your performance. But having those written to disk, then you can actually open your application UI in an offline mode. So you can have this running on production, and if anything happens, you just open that UI and you get the same amount of information that you had from the previous UI. It's basically the same UI. The only thing that will change is the URL. That's it. All right. And yeah, if you guys, so I added this slide just today, just to show the task that we were running. The first example took 18 seconds with some amount of data. Just putting the optimization that you guys see. So putting filter up front, and instead of grouping by doing the combined by key function, we came from 18 seconds to 8 seconds. So I would say having the same calculations being run twice as fast is something worth knowing how to do. The cool thing I've learned recently with one of my friends, actually on a train to Dabax, drinking beer, which was a mistake, was how to look at your Apache Spark code from the perspective of running a JVM process. So there are two tools I just want to guys show you. First one will be JVisualize VM, which you guys probably know, but just quickly. You will see that I have my cluster instantiated on my local machine. So I have a master, I have 2 workers. There's an SBT, but then the same thing I'm doing over here locally, you can do it and connecting by remote to other VM. Just open a port and it will work. So once I run my calculations, 2 new VMs will be created, because Sparks will create new VM each time you run a calculations, because you are saying how much memory the calculations should take. So it will spin a new VM for you. And if we look at it, there's some really cool information that we can get. So how the heap looks like majority of exceptions that you get because you reach out of heap, you will receive out of memory exception. But if, for example, like from the previous version, I think if you were doing group by and your data did not fit, so like you're doing group by key, but on the development environment, like data was not like normalized. It was like straight line. For each key, you have like 1,000 of results, and that worked. But you go to production, and there's this one key that has like 1 trillion of results, and you're doing group by key, and all that data has to fit into the memory. So if it will fit, but it will full like the whole, you see all the add-on generation and the old generation, Spark will not yet tell you I'm out of memory, but it will start triggering GCs one after the other. And from the point of view of the user, you will see on the web UI that there are some problems. There were some tasks being canceled, failed, I'm retrying, I cannot do it without any exceptions. So looking at this code, looking at thread dumps, so how many objects were created, it can give you a lot of sense of what the crazy thing is happening right now within my cluster. And there's the other cool thing. So about Visualize VM, I knew, but how it's called? Java Mission Control, right? Something new added to Java 8. Apparently some additional parameters you have to pay for, but there are a few that you don't have to. It's from this perspective, it looks similar to what we had before. But if we, for example, turn off this memory, tap over here, we get like the whole information about our GC running. So we know like what's the Eden size, what's the old size. So maybe if you guys doing functional programming within Spark, maybe it's doable. I've never tried it, but maybe like increasing Eden size and decreasing old size a little bit, maybe that would help. I don't know, it's something that you can at this point experiment with. But if you're having this problem I was telling you about, so you reach the problem that the moment that application will tell you I'm failing, but I'm still trying, no exception in logs, this is probably where you should go at this point, because you will see those two bars somewhere near 99%, and then you know, all right, probably not enough memory. All right, so few optimization tricks before we finish. Serialization issues, like each data that we push around cluster is serialized, and it's serialized by Java serializer, which is known for not being the best performant serializer that we could have. So they are the ones, so for example, Cryo Serializer has native, they support it natively in Spark, which you can turn on, and it takes a little bit time to configure it because you have to say which class is going to be serialized and stuff like that, but then gives you presumably really good results. There's also a thing called speculation. So if you guys are lucky enough to have your own cluster for your calculations, then you're good. But sometimes you're using Mesos or Yarn, and your job is not the only one that is running within the cluster. So speculation is then something that really, really wise to turn on for a bit. And what it does, Spark will from time to time run the same task for the same partition twice on the different nodes, just to see how each of the nodes were performing. And if it will realize, like out of 1,000 nodes, this one particular node is performing like 10 times worse than the other ones, then it will just simply shut it down. I mean, not shut it down, it will be still running, but Spark will eventually ignore it, seeing there's no point sending any calculations to that node. So if you have a shared cluster, something to consider. Also, the thing that I've learned recently, and I didn't have time to like experiment with it, is that the data that is being shuffled is compressed, obviously, but apparently the codec chosen by default is not the one that majority of developers should use, and there are other codecs to be considered, and they are apparently documented. So it's something worth knowing about, that the way that we compress our data that will be shuffled among the cluster is something to also take into account when creating a configuration. All right, so the next thing is learn your API. So you guys seen that, for example, this thing, group by a map versus combined by key, can give us like real kick. But there are other methods that we should consider and know about. So I've made this mistake. When I first were writing Spark, I just read about some few methods. I knew map, I knew filter, then I read about a few more, and then I just went to do some programming because that's what I like to do. I hate reading documentation. Well, I shouldn't have done that because other methods are quite useful. It's wise knowing what they are doing. So I will give you an example. Map versus map values. Imagine that we have some calculations. We are doing group map, then we are doing group by, and then we have some additional RDD, and we're gonna join those two RDDs by the same key that we are grouping by our first RDD. So with this RDD, the shuffling will occur, obviously, because the data has to fly around the cluster, but Spark will learn that since that data was already shuffled and it's repartitioned properly, it will know that, for example, key, I don't know, A is on that node and key C is on that node. So eventually it will happen the other way around. It will first learn about this, how that is partitioned, and then the shuffling occurring over here will occurring the same with the same partitioner that we have over here. And this is really, really fast. It like gives you like one of the best performance that you will get in Spark is basically because of that feature. But if we run map on, so we had map, group by, and then we joined, right? But we imagine that after the group by, we are doing some mapping because, I don't know, we have a list of, we have array of integers, but we need to run it for array of strings. As I told you before, I said I'm not gonna repeat myself, but I will. Spark will not care what you're doing internally. So at this point, Spark will not know whether you are not messing around with the keys, right? You can eventually, because the not function will be return a tuple, a key, and a value. So eventually you might return a different group, a new key, change key, and a change value. So at this point, it will forget about how your data was partitioned, and if you're going to do join, the shuffling will occur on the both sides. So because of that, we have a method which is called map values, and map values will give you only the value, not the key. So there's no way for you to mess up with the key. So again, you will get the optimized version of the shuffling. Something worth knowing, like few methods within the API that will keep your, so like I told you, like RDD is composed of 5 things. We're talking about 3. Partitioner is the 4th one, and that's the one responsible for this optimization. However, like minority of method calls will actually push that information towards the calculation. So it's something worth knowing which are doing this and which are not. All right. Also understand the basics and like general idea of how Apache Spark calls works. So don't call RDDs within your RDD, because RDD is something to be called on a driver. So like if you wanna do this thing, do that to join, and or Cartesian. The green stuff will work. The red one will give you exceptions. And the last thing before I finish, resources. So Spark Summit Talks, I think the primary resource for you guys. Like essentially the ones that are being created by committers, these are the worth watching. Like I really, really recommend. Also, if you guys don't know, there's going to be Spark Summit in Europe, yay. So something to consider if you're working in Spark, because all the committers will be flying to US to Europe instead of us flying from Europe to US. This book, I think I would recommend. There are the chapters in the book saying like, well, you don't have to read it the first time because this is advanced topic. Those are the chapters that you should read because that's the true knowledge. Other ones you can just skip. Documentation, especially tuning, a lot of stuff I didn't guys tell you about, haven't even time to experiment with it. Mailing list, which I call the place where your problem was already twice or no, 10 times. Right now it's really, really awesome because there are more blogs about Apache Spark, but nine months ago, when I was encountering problem and I tried to Google it, I was waiting for Stack Overflow answer, and there was only 3 results in Google, 2 of them in Chinese, and I was stuck. So mailing list was my main resource to learn about things are happening. Yeah, so my blog is supposed to be having some stuff about Spark, but it doesn't. Oh yeah, so transition from this dude to that dude takes some time. I hope I'm somewhere in the middle. I hope after this talk you guys are somewhere closer to this dude. I would say this presentation has a happy ending, right? I haven't shown you, like I've heard that at least there's one person here waiting for disasters. Like I haven't shown you the disasters, I know. But I'm saying the disasters will happen eventually. Like even yesterday I was preparing some slide and I was fighting with Spark for 2 hours. And I was laughing like, oh my God, I'm preparing like when things go wrong and I cannot fix this one thing for 2 hours, this is crazy. So I'm saying, I know this has a happy ending, but my idea is that eventually we need happy ending in our production software. So what I wanted to show you guys was how to reach the happy ending, even I know with Spark it's sometimes harder than it might seem. My name is Paweł Szulc. I have a blog. I have a Twitter. So if you guys hate it or love it, just tweet. I need to know. We hate it. We love it. That will suffice. And that's a GitHub repo. The code will be there. Maybe not today. Today I'll be drinking beer, but maybe tomorrow. Yeah, and I have still 10 minutes for questions, so if you guys have any questions.
Tell us something about data frames.
All right, so data frames actually a cool thing. So data frames, a new API that was provided, I think, in version 1.3. And what they did is, this is a new API. This is actually a new API that gives you some constraint as a developer. So you no longer manipulate data as it is and do whatever you want. The data is constrained as being somewhat a table with columns and rows. All right. So Spark still doesn't know what the data is. Am I manipulating my bitcoins or porn or whatever? But it knows it has some columns, and if some values at this column, it's probably the same value for, like, it has the same meaning for each of the rows. So imagine that, for example, you have some calculations, and you have table like 25 rows in it, but at the end you're only using 4. So using data frames, Spark will realize that there's simply no point on loading the whole thing, or even shuffling the whole thing. Like if you have column which takes few kilobytes of data, and you have trillions of those rows, and you're not going to use it at the very end, so what's the point of even pushing it through the API? The problem with filter that we saw at the very first example, it can actually do it for you. So if you provide your code where you filter at the very end, internally Spark will put the filter at the very top using data frames only because you were constrained with the API, it can give you some additional optimizations. So something worth using. And I heard, I don't know if it's true, but they're thinking about deprecating RDDs towards data frames. So I would say something to at least familiarize yourself at some point, because Spark is being released every 2 months, so something like that. So at some point we might be reaching a moment with deprecated annotation above RDD. Any other questions? If not, I will be here at the conference. You guys can ask me questions. I'm happy to drink beer, not that much as I did on Sunday, but then again, beer is always good. Thank you very much.